Okay, we're going to take a peek at getting problem number 475 set up. The problem here is at the top of page 214, and it says we want to determine whether the block shown is in equilibrium. They use that term, but it really means, is it at rest or is it moving? And we can determine that by comparing it to the maximum friction force. If you remember, the maximum friction force is the highest value on the friction curve when we have a point. So if we're less than, equal to, or less than the maximum friction force, we are in static equilibrium, meaning we're not moving. But if our friction force is greater than that, then we're on the right-hand side, and now we're in kinetic or dynamic friction, okay? So by comparing it to this, if it's less than Fm, we're at rest. If we're not, if we're greater than Fm, then that means that we are moving. So that's what they want us to do. And they also want us to find the magnitude and the direction of the friction force when theta is equal to 25 degrees and that pushing force P is 750. Okay, so we've got this block on this incline. They're telling us that we do have a weight of this block of 1.2 kilonewtons. So we're going to create the free body diagram. Now, what I did here was I set it up originally based on what was going on the diagram. So if you would, here is the incline, the 25 degrees. I have the 750 Newton force going to the left, and then that would be a 25-degree angle there from its horizontal. The weight of that block is going straight down, so it is a vertical force, 1,200 newtons. And then the friction force, the way that this is held, okay, this P force is pushing. So I look at this like it's going up the ramp. Okay, that's the way. So that would mean if it would have the tendency to go up the ramp if it's moving, then the friction force is going to go in the opposite direction along the surface that it's riding on. So this is the friction force here opposing what we believe is the direction of the motion. And then the last force that we're going to have is going to be the normal force, which is the support force of that block perpendicular to the surface that it's riding on. Okay. Now, as we look here, we have a known force for the weight. We've got a known force for our pushing force. We could put our X and Y axis vertical and horizontal. All right. But then we would have to calculate the components of the friction force and the normal force in terms of their hypotenuse, and then there's more variables to deal with, okay? So what I propose doing is tipping the X and Y axis so that the Y is in line with the normal, and then perpendicular to it is going to be the surface itself that is going to have the friction force on it, okay? And then I'm going to push my forces along their line of action so that we get a diagram that looks like and is a concurrent force system, so that we have the arrowheads of each one of the vectors pulling away from that center. So if we go and we look up here, for instance, this normal force, if this is on the y-axis, I'm simply going to push it so that its tail is going to start at the origin and it's going to pull up on the y. That's why it's here. So this is the y-axis, right? And the x. Then the friction force, I'm simply going to move it along it. So if this is the origin here, and it's going to then pull to the right along the x-axis. Then my 1,200 Newton force, that is 25 degrees from the vertical here. But if I go down, this is going to be here. This is going to be that 25 degrees from the y-axis. So this is the 1,200 newtons with the 25 degrees pulling away from that origin. And then lastly, my 750, move it along through that origin. So it's going to actually start here and pull through. And then it would be on this side here with the 25 from the horizontal. Once we are here, now all you need to do is follow your normal steps. So you're going to calculate any components which are going to be of known forces. So you're going to have actual values of the components. Then you're going to use your equations of equilibrium. Because this is a concurrent force system, it's just going to be sum of the forces in the X and the Y equals 0. Okay. And then you'll be able to solve for the normal force and the friction force. Okay. And then what you're going to do is you're going to compare that friction force then to your maximum friction force. So you have to calculate the maximum friction force. And we know that to be the coefficient of static friction times the normal force. Okay. If it is less than the maximum friction force, then what that means is you're not moving, you're at rest. If it's greater than the maximum friction force, then you're moving. Okay. And then just make sure you answer that question, and that's the process. Is that helpful? Okay. So really kind of getting here, I think is probably like going from the incline or the decline to this. Camden, do you have a question?
Yeah, what's it?
For what? It is going to be the coefficient of static friction times the normal force. And then they're giving you the static friction coefficient and the kinetic friction coefficient. Okay. All right. All right, then that's I think that's a good setup for you guys. I'm going to stop the recording here, but I'll leave this up.